Hey guys, I want to talk to you about some intermolecular forces in this video called dipole-dipole attractions, and we're going to start by talking about a specific type of dipole-dipole attraction called hydrogen bonding. And hydrogen bonding is what keeps water molecules stuck together. I don't know if you've ever really thought about it because we're so familiar with water in our day-to-day life, but it's really kind of weird that liquids like water stick to each other, and it's not just due to gravity, right? When you pour some water out of a bottle, of course it falls out because of gravity, but you get these water molecules stuck together. They don't just spread out all over the place initially. You know, when they hit the ground and form a puddle, it seems to spread out, but the water molecules do just kind of stick to each other. When you look at a wave in the ocean or near the beach, the wave is, of course, created by wind pushing against the water, and eventually, as it approaches shallower depths, you get this wave coming up. But the water molecules are all kind of moving in the same direction, and they're actually pulled along by one another as the wave forms until it starts kind of breaking at the top. Okay. Even without gravity, water molecules stick to one another. I came across a GIF on NASA's website, and I want to show you what water looks like when it's floating around in space. Okay, so you actually get a water droplet even without gravity, and eventually once it stops kind of bobbing around and vibrating, you'll have a perfect sphere of water. So what is it that's causing all those water molecules to stick together? How do they know they're supposed to do that? Why don't they just all fly off and go their own way? Well, if you were listening in yesterday's lesson, it has something to do with intermolecular forces. So were it not for intermolecular forces, each water molecule would go its own direction. Okay, so this particular molecule might be moving that way, and if you've got another water molecule nearby, maybe it's doing its own thing, moving a different direction. Okay, but there is a force that's keeping these things close to one another, and those forces are intermolecular forces. So you have the chemical bonds, which I've drawn in here, which hold the molecule together, but what is it that keeps multiple molecules stuck to one another? That's intermolecular forces, and it has to do with the fact that water is a polar molecule. So water has a net dipole moment. The oxygen atom in water is more electronegative than the hydrogen atoms that it's bonded to, and so these are polar bonds, and the water molecule is a bent molecule. And so you end up with a partially positive hydrogen atom here, another partially positive hydrogen atom here, and then a partially negative oxygen atom. And sometimes people even write two partial negative charges because of the presence of two hydrogen atoms that are bonded to the oxygen. Anyways, we have that net dipole moment thing, right? Okay, with a partially negative end and a partially positive end on the molecule. Okay, but I want to focus on the charges on the individual atoms here. Okay, so when you have multiple water molecules nearby one another, you have the potential for an electrostatic attraction. That means positives attracting negatives. Okay, so right here between these two molecules, you've got a positive charge, partial positive, and partial negative. And positives and negatives attract. Okay, this is not as strong as the chemical bond within the molecule that I've drawn in blue that keeps these atoms stuck to one another. It's not that strong, but there is an attractive force between these two molecules because these are polar molecules. So the hydrogen here can attract the oxygen here. And the oxygen here on this molecule could attract the hydrogen here. and so on and so forth. Okay? And so the oxygen here could also end up attracting the hydrogen over here. And then this molecule would kind of rotate around and get close to this one over here. And they would all kind of line up, and there's different ways you could arrange these things. They could slide past one another and still be attracting one another, and so on and so forth. And it's all about electrostatic attraction, positive attracting negative. Now, this particular type of interaction that I've drawn here is a dipole-dipole attraction, and it's a special strong case called hydrogen bonding. So dipole-dipole attraction is just simply the idea that the dipole in this molecule, two poles, positive and negative, can attract the dipole in another molecule. Right? So the positive on this molecule can attract the negative on that molecule. So this dipole over here, positive and negative, can attract other positively charged or negatively charged things, okay, in other molecules. Okay, so the positive or partial positive on one molecule attracts the negative on another molecule, and it keeps the molecules close to one another. And if this happens over and over and over again, you can have trillions of molecules all attracting one another, and that's literally what you have in this flow of water here. And again, that's what's keeping these molecules all stuck to each other. All right? And it doesn't even, you would never even suspect it's trillions and trillions of molecules. It just looks like one thing on the human scale. It's just a big blob of water. Okay. But of course, if you can imagine if you whacked it with your hand, it would break apart into smaller bits. You could break those apart into smaller bits. Fundamentally, it's composed of many, many, many individual water molecules. All right, so this particular one is called hydrogen bonding, and hydrogen bonding is when it's a special case, and it's sort of a weird name because it's not technically a chemical bond. A chemical bond is what holds a molecule together. Hydrogen bonds are what keep molecules close to one another. In the case of water molecules here, hydrogen bonding is a special, strong case of dipole-dipole attraction. And it happens when inside a molecule you have hydrogen atoms bonded to either nitrogen, oxygen, or fluorine atoms. Okay, you have to have that case. Now the reason is important because hydrogen is the least electronegative element, or non-metal rather, on the periodic table, while those other three elements, nitrogen, oxygen, and fluorine, are the most electronegative. So what that leads to is a strong dipole moment in these bonds. Okay, so you have really, really polar bonds. So that gives rise to very polar bonds. And so what that means is large partial negative and partial positive charges. Relatively large partial negative and partial positive charges. The greater the negative and positive charges that you have, the stronger the attractive force between them. Okay, so if I can get large partial negatives here on one atom and large partial positives on the hydrogens, I'm going to get large intermolecular forces. Okay, so hydrogen bonding is what we have going on here in the water molecule. Okay, you can also have hydrogen bonding between ammonia molecules. Ammonia has this Lewis structure, and even though ammonia is a gas at room temperature, it has that really pungent smell that you can sense if you spray some Windex. If you get it a little bit cold, it'll liquefy. And it'll liquefy rather easily, at the right temperature anyhow, relatively easily. Not as easily as water, because it's a gas at room temperature. But this nitrogen right here has that partial negative charge. I guess you could say 3 partial negative. And then this is partial positive, partial positive, partial positive. This is a trigonal pyramidal molecule. So you have a net dipole moment. And you can get the partially negative nitrogen to attract the partially positive hydrogen on other molecules. Okay? And so that can happen over and over and over again. All right, so again, this is a hydrogen bonding. So hydrogen bonds here, here, there, and so on, okay? Those are the intermolecular forces. Now, what if you don't have one of these 3 elements, nitrogen, oxygen, or fluorine? So for instance, if you're dealing with the HCl molecule, HCl, that's a polar molecule. But because hydrogen is bonded to something that's not nitrogen, oxygen, or fluorine, even though we have a net dipole moment, partial negative, partial positive, okay, so we have those charges present, you do have the possibility of dipole-dipole attractions between molecules of this chemical, okay, right in here. But we're not going to call this a hydrogen bond. This is just a normal dipole-dipole attraction, which is a bit weaker than hydrogen bonding. Okay. If you're confused why this isn't a hydrogen bond because you're seeing hydrogen here, you only grasped part of what a hydrogen bond entails. You need to have hydrogen atoms in your molecule, which you have, there's the hydrogens, but the hydrogens need to be bonded to one of these 3 elements in the molecule in order to get a very polar bond and relatively large partial and positive charges. So since the hydrogen is not bonded to nitrogen, oxygen, or fluorine, you don't have large enough dipole moments in these molecules to get strong attractions between them, okay? But in the HF molecule, if you had a sample of pure hydrogen fluoride, you would have hydrogen bonding that could occur between those, okay? That would be a hydrogen bond. Okay, stronger attractive force than this dipole-dipole attraction. Okay, so one more example to kind of finish up. There's a molecule called oxygen difluoride. Its Lewis structure is like this. Okay, so imagine you had trillions of oxygen difluoride molecules. I want you to attempt to draw where you would see some type of intermolecular force between these two molecules, and whether or not it's a hydrogen bond or just a simple dipole-dipole attraction. So pause the video, draw these two molecules, and then in a different color, try to draw in where you might see an intermolecular force and what type it is. Is it hydrogen bonding or just dipole-dipole attractions? So go ahead, pause the video, and try to answer those two questions. What type of intermolecular force? Where would you see it? Okay, so these molecules are bent, so that means you have a net dipole moment. Fluorine is more electronegative than oxygen, so it would have the partial negative. The oxygen would have the partial positive. Okay, and so if you had trillions of these molecules, all of them would have that type of thing going on here. And so here the partial positive on this molecule could attract the partial negative on that one. So you'd have something like that happening. And this is not a hydrogen bond. It's just simply a dipole-dipole attraction. Okay, so dipole-dipole attraction. So just to recap, we're really familiar with the water molecule because water is all around us. It's so important to human life, to life in general, and to the planet. And it's just amazing how much water is on the planet. And amongst water molecules, you have this special case of dipole-dipole attraction called hydrogen bonding, which is a really strong dipole-dipole attraction. You can also have hydrogen bonding among ammonia molecules or any type of molecule where you have hydrogen bonded to either nitrogen, oxygen, or fluorine with a net dipole moment in the molecule. Now, if you have a net dipole moment in the molecule, but you don't have one of those three elements, or you don't even have hydrogen at all in the molecule, you're only going to get dipole-dipole attractions, which tend to be a bit weaker than hydrogen bonding.